Welcome back, students. In this video segment, we will cover one section, section 6.8. The title of the section is Indeterminate Forms, and it's a French word, L'Hôpital's rule. L'Hôpital's rule. Okay, so this section has to do with a certain way of computing a very important quantity in calculus. So let me pose this question to you. What is the central topic in calculus that separates calculus from all other math, from algebra or geometry or trigonometry or whatever? What is the one topic, one thing that separates calculus from everything else? And if you didn't get it, your hint is it's not the derivative and it's not the integral. Those two things are probably the most important, if not really up there, the most important things in calculus in terms of STEM mathematics, science mathematics, but it's not the central topic. What is the central topic? Well, the answer is limits. Limits. Limits are the bridge from algebra and other math into calculus. So in this section, we look at a very fancy or very specific way of evaluating some kinds of limits. In order to do this, though, we need to go back and talk about what a limit is. The sad fact is that a lot of students forget about this central topic, or never really learned the concept of limit and somehow got through calculus and stuff. So let's take a look at a limit. So the limit, for example, let's find the limit as x approaches 2 of x squared. I think 100% of my students will have no problem getting the answer. What is the answer? And the answer is 4. Now, almost 100% of my students, I believe, will get 4, but I don't think nearly 100% of students will be able to answer the question correctly. The next question correctly is this: does evaluating this limit have anything to do with plugging in or substituting x equals 2? In other words, does this limit have anything to do at all with the function y equals x squared at x equals 2? And a lot of people will say, yeah, well, you just substitute x equals 2. And the answer is no. No, it has nothing to do with what happens with x squared at x equals 2. Nothing. And I know I'm repeating this, but it's a big deal. This limit has nothing to do with x squared at x equals 2. This limit is saying as x becomes infinitely close to 2 without ever touching 2, as x gets infinitely close to 2, what does x squared get infinitely close to? And the answer is 4. Now, the thing that's a little deceiving is we see the equal sign there. This is not saying the function equals 4. This is saying that as x approaches 2, as x becomes infinitely close to 2, as x gets as close to 2 as one would desire, you can make x squared as close as one would desire to 4. You can make x squared as close to 4 as you want just by making x sufficiently close to 2 without ever actually equaling 2. Okay, that's a big chunk to chew, and a lot of people ignore me on this. A lot of students ignore me on this because it looks like, oh, I can just evaluate a limit by ignoring all that mental work and just substituting x equals 2. Well, with that kind of thinking, you join a lot of students who on the first test in calculus tend to get a D or an F. You cannot mentally think x is equal to 2. Okay, so let's move forward. So if you're still not with me on this, it's okay. So let's for our next example, let's let f of x equal a piecewise function, a very simple piecewise function. F of x equals x squared if, let's say, x is not equal to 2, and let's say 1 if x does equal 2. Very, very simple function. So think about what this function looks like without graphing it. I'm going to graph it in a minute, but I want you to think about what this function looks like without graphing it. It's y equals x squared as long as you don't let x equal 2. But if you do let x equal 2, the y value is 1. Well, if we were allowed to let x equal 2 and y equals x squared, we'd get 4. But we're not allowed to let x equal 2 and then substitute it into x squared. When we do let x equal 2, the y value pops down to 1. So what we get is the parabola y equals x squared with a hole drilled in it, if you will, at x equals 2, and the y value replaced with a new y value, y equals 1. If you didn't get that, no problem. I'm going to graph the function. So let's take a look at the graph of the function. Okay, some video magic. Here's a graph of the function. Our usual y equals x squared, parabola vertex at the origin. But as I mentioned, when x equals 2, that y value that would be on the parabola at y equals 4 is removed and replaced with y equals 1. So now the new question is, what is the limit of this function as x approaches 2? Okay, well, I'm going to show you with the use of some red ink here. Observe the graph of the function. As x approaches 2 means x is becoming infinitely close to 2 from either the left or from the right. And as y gets infinitely close to 2 from the left, the y values, look at the y values on the curve, they get closer and closer and closer to 4. As x approaches 2 from the right, the y values get closer and closer and closer to 4. And notice in that discussion, I never mentioned what happens when x equals 2. So the limit of this function, just as it was in the first limit we looked at, is 4. And it has nothing to do with the x value equals 2. Nothing. And I know I keep repeating this, but it's an important thing, extremely important thing. It's the aspect of calculus that separates calculus from algebra. In algebra, we let x equal values, we let the variable equal specific values. We evaluate expressions for x equals whatever, okay, or we solve equations and find that x equals whatever. Here in calculus, we do not allow in the limit x to equal the limiting value, the limit point. We let x approach it without ever touching it. Okay, so follow-up question before we move on. What's f of 2? F of 2 is 1. F of 2 and the limit as x approaches 2 are absolute opposites of one another in terms of what's being asked for. F of 2, it concerns itself only with the y value at x equals 2. The limit as x approaches 2 is the opposite, has no concern about the y value or the x value at x equals 2, but wants to or doesn't want to, but considers what's happening with the y values close to 2. Limits concern themselves with what's happening as x gets close to something. The value of the function is what's actually there. Absolute opposite ideas. Now let me ask you a follow-up question. What happens if the limit of the function and the actual function itself equal to the same thing at the limit point? What do we call that? And the answer is continuity. If the limit of the function equals the actual value of the function at the limit point, you have a continuous function at that point. Okay. Here we don't have continuity. So limits have nothing to do with the value of the function at the limit point, at the point at which we're approaching. Okay, so with that in mind, let's take a look at another review example. All of this is just a review of the first couple of weeks, what you studied in the first couple of weeks of Calculus 1. Let's take a look at the limit as x approaches 3 of x squared minus 9 over x minus 3. A very simple limit. A very simple limit that 40 to 60% of students on an exam, typically on exam 1 in a Calculus 1 class, will get wrong. And the reason for getting this wrong is the idea that we're substituting x equals 3. This limit has nothing to do with what happens at x equals 3. This function is not defined at x equals 3. This function is not defined at x equals 3. So if the limit had something to do with letting x equal 3, you'd have to say the limit doesn't exist, because you can't let x equal 3. However, we're letting x approach 3. As long as we're not letting x equal 3, we can use all the algebra that we learned to simplify this expression before finding the value of the limit. The numerator factors as the difference of squares. The denominator is still x minus 3. Now I can cancel that common factor of x minus 3. As long as I'm not letting x equal 3, I can do that. Well, the limit has nothing to do with x equaling 3. So why not cancel out the x minus 3? We can cancel out the x minus 3 as long as we're not letting x equal 3. We can't let x equal 3. X equals 3 is not in the domain of the function, so it makes no sense to let x equal 3. Okay, so as long as x is not 3, this function simplifies to y equals x plus 3. Now, let's evaluate the limit. As x approaches 3, x plus 3 gets very, very close to 3 plus 3, or 6. Did I substitute x equals 3 into this expression? I certainly did not. Notice my mental step from the second to the last statement. As x approaches 3, as x gets infinitely close to 3, x plus 3 gets infinitely close to 6. And that's why this limit equals 6. Not because we're substituting x equals 3, because we are not. Because if we did, the limit wouldn't have existed in the first place. Okay, so let's look at another common calculus 1 limit. This limit is a limit that a lot of calculus instructors will just have their Calc 1 students memorize. This is an extremely important limit in physics. This is extremely important limit in physics. In the area in physics where you study something called simple harmonic motion or pendulum motion, this limit is important. Okay, we won't go into that example because this is a physics course and it's not appropriate right now to talk about pendulum motion. But so let's take a look at the limit. As x approach, okay, so one of the ideas that you learn in Calc 1 is that when you're evaluating a limit of a quotient like this, a fractional expression, try to let x approach whatever x is going to approach. And if x is approaching something that doesn't involve 0 in the denominator, all we have to do is finish the limit by letting x approach whatever it's approaching in the numerator and denominator. I'll explain. So as x approaches 0, the numerator approaches 0. Sine of 0 is 0. The sign of x approaches 0. And as x approaches 0 in the denominator, x is approaching 0. This is an expression, 0 over 0 is undefined. It is completely undefined. In this section, we have a special name for this form. This is called an indeterminate. Indeterminate form. It means essentially that you can't determine the value of the limit by looking at or trying to simplify 0 over 0. 0 over 0 is undefined. There is no such thing as a fraction with 0 in the denominator, even if there's 0 in the numerator. Okay. In Calc 1, we learned that this limit has a value of 1. This limit has a value of 1, but not because 0 over 0 simplifies to 1. It doesn't. In the previous example, if you look up again, the previous example was of the form 0 over 0. As x approaches 3 in numerator and denominator, we have both numerator and denominator equaling 0, but this limit does not approach 1, it approaches 6. So there's no such thing as 0 over 0. So in a lot of calculus courses, the students are asked to memorize this limit rather than to prove it. A lot of calculus instructors will prove this limit. It requires a little bit of geometry and stuff. We're not going to need that. Our task today is to be able to handle indeterminate forms of this type, 0 over 0, and several other indeterminate forms with some new powerful technique, new to you. Okay. In this technique, we're going to be able to figure out things like, or with this technique, we're going to be able to figure out limits like this one, the limit as x, say, approaches infinity. of the natural log of x. Oh, it looks terrible. Of the natural log of x over x. Now, imagine letting x approach infinity and see if we can evaluate this limit right off. As x approaches infinity, the logarithm, remember the logarithm function goes to infinity very, very slowly. And as x approaches infinity, x approaches infinity. So this is of the form infinity over infinity. This is also an indeterminate form. You cannot determine the value of this limit simply by saying that infinity over infinity equals 1, because there's no such thing as a fraction with either numerator or denominator having infinity in it. There's no such thing as a number with these two numbers, one or both of these numbers in numerator or denominator. So this is indeterminate. If you really think about it, though, we can guess this limit. And I want us to think about it. I want us to think about it right now. It's important to be able to guess this limit. So off to the side, here's the logarithm function, which becomes more and more horizontal as x approaches infinity. So this is y equals ln x, and here's y equals x. Both y equals x, the denominator function, and y equals natural log of x, they're approaching infinity. But look what happens for large values of x. The logarithm seems to trail y equals x. Y equals x still keeps getting bigger and bigger and bigger at a constant rate. The rate would be the derivative. Rate of y prime is 1. So for every x increase in 1, the y increases by 1 and y equals x. But log of x, the derivative is 1 over x. So it levels off. Remember, the slope of the tangent line is the derivative, and 1 over x approaches 0. So true, both numerator and denominator approaching infinity, but the numerator is getting there very slowly. So the numerator is going to infinity very slow, while the denominator is getting there very quickly comparatively. So the denominator gets big much faster. What do you expect this limit to be? Think about it. Denominator gets huge much faster than numerator. So this should go to 0. We don't have to rely on our intuition for that. We're going to prove that in a few minutes. Let's take a look at another limit. We're going to revisit these limits with this new technique. I haven't shown you the technique yet. The limit of e to the x over x. Now, this is also indeterminate. This is of the form infinity over infinity. But remember, the exponential function grows extremely quickly. The opposite of, if you will, of how the natural logarithm grows. I'm going to draw the exponential function in green on the graph. It grows very, very, very quickly. Compared to y equals x, the natural logarithm function approaches infinity much more quickly. So what would we expect when you divide the two numbers, e to the x by x? You should get a fraction that's blowing up in the numerator much more quickly than the denominator. So that you would expect the limit to be infinity. Again, our intuition doesn't need to be real powerful with that yet. Toward the end of the course, that kind of intuition is what's going to get you through. Actually visualizing how fast numbers get large and stuff. But right now, we have a formula to help us out. Okay, this formula lets us evaluate limits of certain indeterminate forms. So let's take a look at this formula or idea. Okay, so here's the rule. It's named after a Frenchman. I don't know any French, so I don't, including French grammar and stuff. So the name, I do know the name of the rule though. It's called L'Hôpital's rule. L'Hôpital's rule. And some textbooks spell it the way I did. Our textbook spells l'hôpital as if the word hôpital was hospital. And apparently, that's how you say hospital in French, is hôpital. And the S is not pronounced, so sometimes it's spelled without the S. In any case, it's called L'Hopital's rule. And it goes like this. Suppose that we have a limit. So if the limit as x approaches some number a of f of x over g of x is of one of the two indeterminate forms, and only these two limit indeterminate forms are possible, 0 over 0 or infinity over infinity, then the original limit, the limit as x approaches a of f of x over g of x, is equal to the limit as x approaches a of the same quotient, but with derivatives instead of the functions, f prime of x over g prime of x. This isn't the quotient rule. This is just take the derivative of the numerator and derivative of the denominator and take the limit. This is amazing. It's an amazing thing. You divide y values, that's the functions, and let x approach a, you get the same thing as if you divide the slopes of the tangent lines. That's absolutely amazing. Okay. Now I've also written in parentheses below it part of the rule, and I wrote it in parentheses because this statement is not going to affect us. The statement says, provided the limit on the right, that means the limit with all the derivatives in it, or both the derivatives in it, exists or equals either infinity or negative infinity. This is always going to be the case for our course, for us. So you can think about this as if the limit is of the form, one of the two indeterminate forms that we've talked about so far, 0 over 0 or infinity over infinity, then the limit of the original function, quotient, is equal to the limit of the quotient of the derivatives. That's amazing. Amazing. It's something that if we had in Calc 1, it would have made our lives a lot easier. Well, so why didn't we give it to you in Calc 1? Because when we were talking about limits in Calc 1, they predated the existence of derivatives for you. They came long before derivatives. Okay, so let's go back to some of those limits we were looking at before. So let's evaluate some limits, a bunch of limits, including those that we were looking at earlier, including the one we could evaluate very simply using some algebra. Limit is as x approaches 3 of x squared minus 9 over x minus 3. Okay, so in order to use this L'Hopital's rule, you first, don't skip this step. It could really ruin you. And with these problems, just skip the step of determining that the form is indeterminate. So you first determine, is the form indeterminate? Well, as x approaches 3, x squared minus 9 approaches 0, and x minus 3 approaches 0. So this is indeterminate. Once we determine that we have one of these two indeterminate forms, either 0 over 0 or infinity over infinity, we can apply L'Hopital's rule. So this equals, and I'm going to ask you to, when you use L'Hopital's rule, draw a little, at least an L over your equal sign or an L apostrophe H only at the moments where you use L'Hopital's rule. So by L'Hopital's rule, the derivative of x squared minus 9 is 2x. The derivative of x is 1. And then we recheck this last limit to see what its limit is. If we need L'Hopital's rule again, or if we can just evaluate the limit. Well, as x approaches 3, 2x approaches 6. So the value of this limit is 6. I didn't write a little L apostrophe H over this last equal sign because I didn't use L'Hopital's rule again. I just used Calc 1. Okay, so every time you use L'Hopital's rule, write a little L or L apostrophe H above the equal sign. The next limit, which is the one that we very often see our students just asked to memorize without proof, is the limit of sine of x over x. Okay, well, first determine whether the thing is indeterminate or not. The limit's indeterminate. It is. The sine of 0 is 0 and x equals 0. So the sine approaches 0 and the denominator approaches 0. So this is indeterminate. So we may apply, and we will apply, L'Hopital's rule at this juncture, at this stage. So this is the limit using L'Hopital's rule as x approaches 0. Don't skip the putting in limit x approaches 0. The derivative of sine is cosine. The derivative of x is 1. And now check this limit. As x approaches 0, the cosine of x approaches cosine of 0, which is 1, and we get this limit instantly. This is amazing. This device, this discovery is amazing. Let's take the limit of, as x approaches infinity, the natural log of x over x. Now we guess that this limit is 0 because the logarithm goes to infinity very slowly compared to y equals x. Well, so we determined that this is one of the two forms. This is the second form, infinity over infinity. So let's apply L'Hopital's rule to this. So if we apply L'Hopital's rule, the derivative of the natural log of x is 1 over x. The derivative of x is 1. You probably get this last limit without doing another step, but I'll put 1 in. If you remove the over 1, as x gets big, as x gets large, 1 over x gets small. So this limit is 0, okay, which is what we expected. We also looked at comparing. Basically comparing the exponential function e to the x with x. So first determine that you have an indeterminate form, or if you don't just use Calc 1 or whatever to evaluate the limit. So this is one of the two indeterminate forms. So this, by L'Hopital's rule, becomes the limit as x approaches infinity. The derivative of e to the x is e to the x. Now this is over. As x gets large, e to the x gets huge. So this limit is infinity over 1 or infinity. Okay, let's do some more. E. Let's see how e to the x compares in this fashion with a function that grows faster than x squared. Okay, so now we're comparing the exponential function with y equals x squared. Okay, now we're getting a different situation. As x gets large, both the exponential function and y equals x squared get large. So do we still get infinity, or does x squared catch up with e to the x as x gets large? Well, we don't have to rely on our intuition for this. This is infinity over infinity. As x gets large, e to the x gets large, and so does x squared. So I'm going to apply L'Hopital's rule to this limit. So this is limit as x approaches infinity. The derivative of e to the x is e to the x. The derivative of x squared is 2x. Okay. Well, what are we looking at then? Well, e to the x over 2x, as x gets large, e to the x is still approaching infinity, and 2x is approaching infinity. So it appears that L'Hopital's rule didn't work. We still have an indeterminate form. Well, it's fine. We still have an indeterminate form, so apply L'Hopital's rule one more time. Apply it as many times as is necessary sometimes. So the derivative of e to the x is e to the x. The derivative of 2x is 2. This is no longer indeterminate. This is of the form infinity over 2. What's half of a large number? It's large. Half of infinity is still pretty big. Okay. Okay. So in fact, it wouldn't matter what the exponent was in the denominator. If I had x cubed in the denominator, and I took the derivative, I would get 3x squared, which still goes to infinity. If I took the derivative of 3x squared, I'd get 6x, which still goes to infinity. If I took the derivative of 6x, I'd get 6. If you didn't get that, you can always skip through this example if you know what I just said. X cubed. This is infinity over infinity. It's indeterminate. Use L'Hopital's rule on it. X approaches infinity. Derivative of the numerator. Derivative of e to the x just stays e to the x, but the powers get smaller and smaller as you take derivatives of the denominator. Limit as x approaches infinity of e to the x over 6x. This is still infinity over infinity. L'Hopital's again. Limit as x approaches infinity of e to the x over 6. And it's over. This is not of the form 0 over 0 or infinity over infinity. Those are the only two indeterminate forms possible for which we could use L'Hopital's rule. This is e to the x is going to infinity, and denominator is 6. What's 1/6 of infinity? It's still pretty darn big. So this limits infinity. In fact, e to the x grows faster than any power. And large powers grow fast. X to the 100th power shoots up extremely quickly after x equals 1. But if we take enough derivatives of x to the 10th, we'll get a constant in the denominator. So e to the x over any power of x eventually will approach infinity. Okay. Another example. This next example is a cautionary example. Let's take a look at the limit as x approaches 0 from the right of the natural log of x over x. Okay. The biggest mistake, or the mistake that's made with this limit extremely commonly, is for students to believe that this is indeterminate and apply L'Hopital's rule. What's happening to this function as x approaches 0 from the right? As x approaches 0 from the right, the logarithm's approaching negative infinity. Let's look at the graph of the logarithm above. As x approaches 0 from the right, the logarithm approaches. I'm having a hard time doing this with my phone's ringing here. Sorry, students. Okay. Easier just to not edit that out. The logarithm, here's the logarithm. As x approaches infinity, look up at the graph. The logarithm shoots down. I'm writing a little green arrow to negative infinity. Note to self, unplug landline next time I record a lecture. Okay, so the logarithm is approaching negative infinity. As x approaches 0 in the denominator, x is approaching 0 in the denominator. So this is infinity. This is of the form infinity over 0. 0 from the right, if you will. Well, let's mess around with that fraction. It's not really a fraction because you can't have 0 in the denominator and you can't have infinity in the numerator. But let's mess around with it a little bit. If you don't see what this limit is, the numerator is getting huge but negative, and you're dividing by small. When you divide by small, you make big. That's the big little principle from pre-calc. If you divide by small numbers, you get something big. So you're dividing negative infinity, which is already pretty big, by something small. It makes it even bigger. If you don't see this, there's a little trick. You can write this as negative infinity times 1 over 0. This is almost always forbidden in textbooks, but it works real well. We can treat this like fractions in this case. And we have negative infinity, and then think about the big little principle from pre-calc. 1 over small, that's 1 over a small positive number, 1 over 0 plus. 1 over a small positive number is large and positive. And negative large number times a positive large number is a negative large number. This limit is infinity. And this explanation is perfectly fine. This limit is not indeterminate. Not indeterminate. You may not use L'Hopital's rule for this problem. Okay, you may not use L'Hopital's rule unless it's of the form infinity over infinity or 0 over 0, just to make sure you're okay with that fact. Let's do a simple limit. Let's take a look at the limit as x approaches 4 of x squared, that same function we looked at earlier, x squared minus 9 over x minus 3. You can't use L'Hopital's rule on this because the numerator and neither numerator nor denominator are approaching 0 or infinity. We need 0 over 0 or infinity over infinity. So let x approach 4. As x approaches 4, x squared approaches 16. As x approaches 4, the denominator approaches 4 minus 3. So 16 minus 9 is 7 over 1. This limit is 7. No L'Hopital's used. So don't just start using L'Hopital's rule every time you see a fractional expression, okay? the function you're evaluating the limit of must be indeterminate. Must be, okay? Okay. There are times when L'Hopital's rule, the use of L'Hopital's rule isn't so straightforward. We may only use L'Hopital's rule when we have the forms 0 over 0 or infinity over infinity. We need to have the expression, the functions we're evaluating the limits of in this form before we can apply L'Hopital's rule. So sometimes the functions are not in this form. So we need to identify what other indeterminate forms are. That means forms of the limits of functions that cannot be evaluated simply by letting x approach whatever we're approaching, and then how to make them appropriate for L'Hopital's rule. So other indeterminate forms. Other indeterminate forms. Determinate forms. To help you along with this, think about infinity as being a large number. How large? Well, infinitely large. And think about 0 as being small. 0 plus being small positive. 0 from the left, small negative. How small? Infinitely small. Well, just to help us along though, let's think about them as actual specific small, negative, small, positive, small numbers, large numbers, okay? So, is this form indeterminate? Infinity times infinity. And the only thing you have to do to answer that question is answer the question to yourself. What's a large number times a large number? If you multiply a large number by a large number, you make the result even bigger. So this is not indeterminate. This is not indeterminate. Determinate. The limit, for example, of x cubed times 1 plus 2x as x approaches infinity. This is not indeterminate. X cubed is getting large. 1 plus 2x, 2 times a large number, large, at plus 1 is even larger. The value of this limit is just infinity. Okay, so this is not indeterminate. How about a large number plus a large number? Think about it. If you have a large number and you add more of anything to it, it's not indeterminate. It's large. This is infinity. This is not indeterminate. This is also infinity. Indeterminate. Okay, so now we get to question, well, what is indeterminate? What do you get when you take a large number and you subtract another large number? And the result that students who don't think about it, who don't think about this carefully, will say, oh, 0. Well, really? What if I take 6 times 10 to the 23rd power? If you've had chemistry, that number should ring a bell. That's 6 times 10 to the 23rd power. That's 6 followed by 23 zeros. And you subtract, let's say it's a billion. I'd love to have $1 billion. $1 billion is 1,000 millions. Well, 6 times 10 to the 23rd, that's a large number, minus $1 billion, that's a large number. This is still approximately what? This is still approximately 6 times 10 to the 23rd. If you remove $1 billion from 6 times 10 to the 23rd, you're not removing very much relative to how big 6 times 10 to the 23rd is. So in this case, large times minus large is still large. So large minus large can be anything. So it is indeterminate. This is indeterminate. And by large minus large, I don't mean specific large numbers. I mean functions that are approaching infinity minus another function that's approaching infinity. I can't write and talk at the same time. Indeterminate. Okay, so what am I talking about here specifically? Let's take a look at the limit. Let's say as x approaches pi over 2 but creeps in from the left of secant x minus tangent x. The amount of trig that we're going to see in this course is about to explode in the next few sections, so we might as well start getting some trig in there. We're going to see trig come back in this course like never before. Okay, so we might as well start getting ready for that here. So, well, let's let x approach pi over 2 from the left and see what's happening with secant, and see what's happening with tangent, see what's going on. Okay. Off to the side, I have graphed for us the secant function and the tangent function, half a period of the secant and a full period of the tangent function, and included the neighborhood near x equals pi over 2. So let's take a look at what's happening here. As x approaches pi over 2 from the left of the secant function, little arrows there on the secant now in red, the y values are becoming infinite. So this limit is of the form infinity minus, and the same thing's happening with the tangent. As x approaches pi over 2 from the left, the tangent is becoming infinite. This is an indeterminate form. We can't conclude that just because these two functions are becoming infinite, that when we subtract them, we get 0. So here's the big question. How do we use L'Hopital's on this? The answer is we don't. Not yet. We can only use L'Hopital's rule in the cases where we have infinity over infinity or 0 over 0. So we mess with the function. We mess with the function by using some algebra, sometimes a lot of algebra, trigonometry, identities, whatever we have to get this function into the form 0 over 0. Or infinity over infinity. So the secant function is 1 over the cosine. The tangent function is sine over cosine. So this function then becomes the limit as x approaches pi over 2 from the left of 1 minus sine, the same denominator of cosine, so over cosine. Now we don't just randomly apply L'Hopital's at this point. We make sure that we can. So as x approaches pi over 2 in the numerator, the sine is approaching 1. The sine is approaching the sine of pi over 2, which is 1. And 1 minus 1 is 0. As x approaches pi over 2 from the left, or through any direction, the cosine, from either direction, the cosine is approaching 0. So this is indeterminate. So at this point, we apply L'Hopital's. So this is the limit as x approaches pi over 2 from the left. The derivative of the numerator, derivative of 1 is 0. The derivative of sine is cosine. So we get negative cosine. And the derivative in the denominator, derivative of the cosine is negative sine. Now we check this limit. If it's indeterminate, we may apply L'Hopital's rule again or use algebra if we want. Or we just plug in not plug in there, I almost fell for it. We let x approach pi over 2 from the left. Well, as x approaches pi over 2 from either direction, the sine is not approaching 0 anymore, it's approaching 1. And as x approaches pi over 2, the cosine is approaching 0. Look at the graph of the cosine. Okay, so this limit has a value of 0. The value of this limit is 0. Okay. So if you have an indeterminate form like infinity minus infinity, you memorize it. Infinity minus infinity is indeterminate. If you have an indeterminate form, infinity minus infinity, you transform it into one of, if possible, into one of the two allowable forms for L'Hopital's rule. Okay, so how about let's take a look at the possibility of some more indeterminate forms. How about infinity times 0? A large number times a small number. Remember, 0 we're not interpreting as the number 0. We're thinking about it as a small number. And these aren't numbers. These are functions approaching 0, functions approaching infinity. So if you have a function which in the limit approaches infinity times another function that in whose limit is approaching 0, what do we get? And the answer is indeterminate. You cannot say that a large number times a small number is either large or small. In fact, a large number times a small number can be anything. Examples? What's the limit as x approaches infinity of x squared times 1 over x? Well, we can evaluate this limit real simply. But what's going on? The first function, x squared, is approaching infinity. The second function, 1 over x, is approaching 0. So we have infinity times 0, so we have large times small. Well, what does this limit equal? This doesn't take rocket science. I guess we're not studying rocket science at all, so don't worry. X squared times 1 over x is x. As x goes to infinity, we get infinity. So in this case, big times small, infinity times 0 is big. Infinity times 0 turned out to be big. Well, what if we have the limit as x approaches infinity again, x times 1 over x squared? What are we looking at? The first function is approaching infinity. The second function is approaching 1 over infinity squared. That's small. So this is big times small again. What does this actual limit equal? Well, let's simplify using some algebra. Not a lot of algebra. This is a very simple limit. X times 1 over x squared is 1 over x. As x gets big, 1 over x gets small. So in this case, big times small approaches 0. Now I said you can make big times small approach anything. Not just infinity or 0. You can make it approach anything. Think of a number between 1 and 10. I guess I can't ask you to give me that, huh? I'll come up with one for you. Pi. I didn't say think of a whole number. But think of a number between 1 and 10. There are a hell of a lot of choices for these numbers. Say pi. Well, let's take the limit of x squared. And you could think of it anything you want. Pi, e, 5, 7, 9, 1.3, whatever. I'm using pi. So pi. And let's take the limit of x squared times pi over x squared. As x gets big, x squared gets big. As x gets big, as x goes to infinity, pi over x squared gets small. What's the limit of this function? It's not big times small is 0 or big times small is infinity. What's big times small approaching? Well, what do x squareds do? I made big times small approach pi. You can replace that little red pi in there with e, 1.7, radical 5, anything you want. So my big point here is that infinity times 0 is indeterminate. Okay, so for example, what if we have, I keep forgetting to write for example in my examples here, so forgive me. Please, as x approaches infinity, let's say square root of x times e to the minus x over 2. Okay. Well, let's see what kind of form we have here. As x approaches infinity, the square root of a large number is still large. And as x approaches infinity, we're looking at e to the minus infinity over 2, e to the minus half of infinity is infinity, e to the infinity is 1 over, e to the negative infinity is 1 over e to the positive infinity. That's 0. So this is the large times small problem. This is indeterminate. Now remember, just like the infinity minus infinity case, we can't apply L'Hopital's rule directly to this indeterminate form. We have to, if we're going to use L'Hopital's rule, we have to transform our function into an indeterminate form where the limit of the function is indeterminate of one of the two indeterminate forms, either infinity over infinity or 0 over 0. Now, that e to the minus x over 2, I can pop into the denominator. I can write it in the denominator with a positive exponent. How did I do that? Algebra 1. Negative exponents can be written as positive exponents in the denominator. Okay, so no real mystery here. Now re-examine this limit. As x goes to infinity, the square root of infinity is infinity over e to the infinity over 2. E to half of infinity is still e to the infinity, which is infinity. This is indeterminate. Bottom line with these non-standard, non-0 over 0 or non-infinity over infinity indeterminate forms is you must manipulate your function into being one of the two standard forms, 0 over 0 or infinity over infinity. Then you're free to use L'Hopital's rule. So using L'Hopital's rule, well, recall the square root of x means x to the 1/2 power. So if I take the derivative, I have 1/2 x, bring down the 1/2, decrease the power by 1. Now the derivative of e to the 1/2 x is e to the 1/2 x times 1/2. The derivative, chain rule, derivative of x over 2 is 1/2. Okay, now you're not bound to using L'Hopital's rule just because you end up with a fractional expression. So let's see if we can evaluate this limit. Let's do a little algebra. Let's perform a little algebra on this. 1/2s cancel. That x to the negative 1/2 in the numerator can be brought down in the denominator as x to the positive 1/2. Funny looking x there. Let me see if I can clean up that denominator. It looks pretty ugly. That's better. If you don't see it yet, this is the limit as x approaches infinity of 1 over the square root of x times e to the x over 2. It's over. The square root of infinity is infinity. Square root of a large number is large. E to a large number is large. Large times large is even larger. This is 1 over infinity. This is 0. Okay. Okay. So let's take a look at one more set of indeterminate forms all at once. The following are indeterminate forms we've looked at so far. 0 over 0, infinity over infinity. Those are the standards. Infinity minus infinity, and infinity times 0. These are all indeterminate. There are 3 others that pop up, and we're not going to look at justifying them the way I did with infinity times 0. Just remember that these are indeterminate. 0 to the 0 is not 1. Infinity to the 0 is not 1. It's indeterminate. And 1 to the infinity you would think is 1. It's indeterminate. These are all indeterminate forms. These are all indeterminate. All of them. Okay, so I want to look at, to end our lesson for this section, I want to look at a form, and this limit's very important for us. It's going to hold together a lot of our work toward the end of the session. I want to look at a limit of the form 1 to the infinity. When we're done with this limit, you should memorize this limit. It's going to pop up, like I said a couple seconds ago, in a whole lot of the end of our semester. Let's take a look at the limit of 1 plus 1 over x. Not just that. As x approaches infinity, that would just be 1. Not just that, but I want to raise that to the x power. As x gets large, the inside the parentheses is approaching 1, but the exponent's approaching infinity. This is indeterminate. This is one of the indeterminate forms. Don't state that the value of this limit is 1. The actual value of this limit may surprise you. Unless you already know what the limit is. Okay. So the trick is to let y equal the function whose limit we're evaluating. And we want the limit as x approaches infinity of y. Okay? So the reason we're doing this is we're going to do something similar to what we did earlier in the course with logarithmic differentiation. I want that exponent down. So I'm going to take the natural logarithm of both sides. Okay. Then I'm going to use the third of the big three properties. Brings the exponents, turns them into coefficients. Now this isn't our original function. This is the log of our function. So I'm going to take the limit of both sides as x approaches infinity. I want the limit of y, but I'm going to be satisfied with the limit of the natural log of y. Now, how could I get the limit of y out of this? Think about it. If I take the limit of the natural log and I get some number, how do I get the limit of the function without the natural log? What cancels out the natural log? Take e to both sides, exponentiate. If you missed that, don't worry about it. It was just sort of a preview. Let's take the limit of the natural log of y. Let's see what kind of form we have. As x goes to infinity, that little guy x is approaching infinity. As x approaches infinity, now let's take a look at the log of 1 plus 1 over x. 1 over x is approaching 0. So the log of 1 plus 1 over x is approaching the log of 1, and the log of 1 is 0. So this whole other piece is approaching 0. This is indeterminate. But it's not one of the two that we need. So we manipulate, and sometimes this manipulation can be a little tricky. When we manipulate our function, whose limit is indeterminate now, but not of really the right one for us, we convert it to one of the two standards, infinity over infinity, or 0 over 0. So now see that x over 1? Now see that x isolated in the limit? I can write it as 1 over x in the denominator. That was tricky. What did I do? Off to the side. X over 1, I want the x in the denominator, is the same thing as 1 over 1 over x. That's all I did. Is in the limit, just a couple lines up, that x that I circled in green is x over 1. So I want it in the denominator, so I put it in the denominator as 1 over x. This trick is really nice, really nice. Now reevaluate this limit for its form. I'm going to move this thing out of the way. All right. I'll get rid of it then. Okay. Okay, let's see what kind of form we have here. As x goes to infinity, 1 over x approaches 0. Log of 1 plus 1 over x approaches log of 1. Log of 1 is 0. In the denominator, 1 over x approaches 0. Now we can apply L'Hopital's rule. So we will. L'Hopital's at this stage. This is the limit. X approaches infinity. The derivative of natural log is 1 over 1 plus 1 over x. That's the derivative of the natural log of 1 plus 1 over x. But the chain rule says we need to multiply by the derivative of 1 plus 1 over x. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. Then you do the same thing in the denominator. The derivative of 1 over x is negative 1 over x squared. That's convenient. That's convenient. Negative 1 over x squared cancels out. It's extremely convenient. So we're just looking at the limit as x approaches infinity of 1 over 1 plus 1 over x. That's easy. X gets big, 1 over x approaches 0. 1 over 1 plus 0 is 1. Now that's not what we were asked for. We're looking for the limit of y, not the limit of ln y. This says the limit of ln y as x approaches infinity is 1. So let's find the limit of y. Take e to both sides. Exponentiate. Exponentiate. Factor out the limit process on the left. E and ln cancel, so we have the limit as x approaches infinity of y equals e. So this limit is important. It's a strange limit that holds together a whole lot of our stuff at the end of in the end of the course. The limit of 1 plus 1 over x raised to the x as x approaches infinity is e. I think it would be a real good idea for you to memorize that limit. Okay, real important. Okay, well, that takes us to the end of section 6.8. And go ahead and feel free to dig into homework whenever you get a chance. And I'm looking forward to talking with you all again soon.